Good afternoon, not good afternoon, but right, we are going to look at this thing called linear algebra, but our university looks at linear algebra in different ways. So we are not going to do the whole syllabus of the linear algebra, but we are going to start where it says the rank of a matrix. Right. Now, what is the rank of the matrix really? A rank of a matrix is how many independent rows or columns does the matrix have? That is the definition of the rank. It's how many independent rows or columns does the matrix have? Though not these type of hard ones. I know there are hard definitions, but just know that the rank of a matrix is how many independent rows or columns a matrix have. So let's look at this concept of linearly independent. Right, independent. I don't know how to write these words. I'm a mathematician after all. So just know that. Linearly independent. Let me give you matrix A. I have matrix A, which is 1, 2, 0, 4. And again, matrix B, which is 1, 0, 3, 1, 1, 1, negative 8, 2, 8. Right. This A and B are given as matrices. Now, if you can take note, you can note one thing there, that you have row 1 on top, and then we have row 2 on the bottom, row 1, row 2, row 3. Now, if you can take note, this entire row at the top, which is row 1, is different from this entire row from row 2. Now, the concept of linearly independent means row 1 does not share a factor or a number, multiple to row 2. There is nothing that you get from row 1 you will also get on row 2. There is no factor that you say to get row 2 you need to multiply the first row to get row 2. There is nothing like that. Let us look at the second matrix P. You can notice that the rows are different also. The rows are also different. You can also note that the columns are also different from one another. So we can deduce that the rank of this can be what? Right, for a 2 by 2 matrix, the rank of A is equals to 2. The rank of A is equals to 2. If you're going to do this thing of rows which is linearly independent, and the rank of B is 3, because there are 3 rows which are not the same really, but they do not share a factor. Right. Let us look at another concept, which is linearly dependent. Linearly dependent. When we say rows are linearly dependent, we mean this. Let's have matrix A. I'm going to think of any number order. -5, 3. And then I am going to multiply the first row with the -2. If I multiply the first row with the -2, I'm going to have 10 as a second row, and I'm going to have -6. Right? Let's look at matrix P, which is a 3 by 3, 1, -2, and 3, 4, 8, 5, -3, 6, -9. Right. You have those, you have those matrices. You have those matrices. Now, how can you spot that these rows actually are linearly depending to one another? Now we have row 1, you have row 2. You have row 1, you have row 2, you have row 3. Right? So, for matrix A, deduce something that is very important. We say row 2 equals -2 row 1. To get row 2, you need to multiply -2 on row 2. You need to multiply -2 on row 1 to get the second row, right? To get the second row, you need to multiply -2 on the first row. Now, because we have this case, row 2 depends on row 1. Here we have something called linearly depending, a row that is depending on another row. If you have this case, the rank of A, it is a 2 by 2 matrix -1. Now this -1 comes from the fact that there is a row there which is the same with the other row. It's just that that row is been multiplied by -2. So we remove that row. For example, we are going to remove this row. Now, to find, now the rank there, it's going to be what? To be 1, because there's only one row in that matrix. So it's going to be 1. Right? I didn't do this for the fact. I didn't do that. So let us look at for matrix 2, for matrix B. For matrix B, you can clearly see that for matrix B, to get row 3, you need to multiply by the -3 on the first row. So R3 is actually -3 row 1. Now, if you have this case, row 3 depends on row 1, because both of these rows share a factor of -3. Any questions? If there are no questions, you can plug them in the comments. Right. So what can we say here? Because the third row is depending on the second. The third row is depending on the first row. We quite remove the first row, the third row. And how many rows do we have? We have 2 rows. So the rank of B is actually 2, because there are 2 rows there which are linearly independent. Right. Now, in an exam, you will not see this thing of row linearly independent and thing. But what we are going to do, we are going to look at a property or another method that we are going to use. It's called the determinant method. It's called the determinant method. right? In the determinant method, it's very simple. Given, I'm just going to lay out the properties of this, and then we are going to look at the problem. Now, given matrix A of order n by n, which means this is a square matrix. This is a square matrix. Because this is a square matrix, we are allowed to find a determinant. Now, condition 1. Condition 1. Now, if the determinant, which is represented by det absolute A, is not equals to 0. If the determinant is not equals to 0, we will say that the rank of the matrix A is equals to n. Now, this n is actually the order of the matrix is equals to n, which is the number of rows and the number of columns, is equals to the rank, which is equal to the number of rows or the number of columns that you have. Is equal, the rank of A is equals to n, and the matrix A is non-singular, and matrix A can take an inverse. This matrix can take an inverse because we are going to the concept of diagonalization. We need to know what type of matrices that you can take the inverses. The type of matrices that you can take the inverses are the matrix that if you find their determinant, the determinant is not equals to 0, right? So this is the first condition, right? If the determinant of A is not equals to 0, your rank automatically becomes n, which is the number of rows or the number of columns that you have. The matrix A is non-singular, and that matrix of A can take the inverse. All right, let's look at condition 2. Condition 2. Condition 2. Now, what is condition 2? If the determinant of A is equals to 0, the matrix is non-singular. The matrix cannot take the inverse, or some say invertible. It's not going to take the inverse, and the rank of A is equals to n minus 1. Now remember, if the determinant there is going to be 0, your rank will become n minus 1 for a matrix of n by n. Your n is the order, or it's the order, and it's the number of rows to the number of columns. So because this is a square matrix, the number of rows is equal to the number of columns, which is an n by n. And you need to know that this value of n here, this value of n will be subtracted by 1, because it means that there is a row here which depends on the other row. Well, what is this? On the on a particular row. Right, so there is a row here that is depending on a particular row, so that's why we say that rank is n minus 1. Now let's look at an example of two matrices. Matrix A, the equation: find the rank of the following matrices. Now I'm going to give you matrix A first, which is 3, 0, 9, negative 6, 0, negative 18, and 8, 4, 1. Matrix B, it's going to be 1, 0, 3, minus 5, no, just written it wrong. It is 1, 3, minus 5, 6, minus 5, 8, 1, it's 7, sorry, 1, 0. So that is the matrix that you're going to have, right? So now how do you find the rank? Start with matrix A. We need to find the determinant. So to find the determinant of a matrix, use a column or a row with the most 0. Any column that you prefer there. Any column that you prefer, you'll find the determinant. I am going to use the first row and the second column. This is C2, that is row 1. So I'm going to use them both. You will see what do I mean that you get the same answer. So let us use the first row. I'm going to set the determinant of A. If you use the first row, you know the rules. Actually, you know the rules. 3, cover this row, cover the first row, cover the first row, cover the first column. I'm going to have 0, minus 8, 4, 1. Because there is a 0, so I'm not going to include the 0 minor. Plus 9. Plus 9, minus 6, 0, 8, and 4. Your determinant of A, it's actually going to be 0. Because there are two rows which are the same. Your determinant there, it's going to be 0. Even if you use this row, even if you use this column, if you use the second column, the determinant of A, it's going to be minus plus minus, which is going to be minus 4. If you cover the second row and the last row, I'm going to have 3, minus 6, 9, and negative 18. You are going to have again 0 here because this matrix, the square matrix, is going to be have 0. Because the determinant here, it is 0. Because the determinant here, it is 0. We cannot just go straight away and say that the rank here is going to be 2. We cannot do that because we are using a determinant method that has two conditions. We cannot just say that the rank here now it's going to be 2. Because we know that the determinant of this matrix is a row that is linearly dependent on another. What the method is, you need to try to find a matrix here, which is a 2 by 2 matrix inside matrix A that we can give you a matrix which is not equal to 0. Now you can really see that 3, 0, negative 6, 0 can give you 0. 0, 9, 0, 18 also can give you 0. Minus 6, 0, 8, 4 cannot give you 0. And 0 minus 18, 4 and 1 cannot give you 0. I'm going to take out a matrix Lapana on A that can never give you 0. So matrix A1, it is negative 6, 0, 8, 4, or matrix 0, negative 18, 4, 1. Even though these two matrices, which is going to be A2, even though these two matrices cannot give you the same answer, the important thing here is to know that whenever you whenever you take out a matrix, you always going to take out a matrix, only one matrix that can give you an answer of 0. So I'm just going to pick A1. So picking A1, I'm going to have the determinant of A1 is equals to minus 6 times 4 minus 0 times 8. Your answer there is negative 24. Since we got our determinant of not equals to 0 on a 2 by 2 matrix, we say that the rank is equals to 2. Do you understand? Because we got our determinant on a 2 by 2 matrix, which was negative 24, our rank of matrix A is going to be 2. Because the order of a matrix that we got the determinant was a 2 by 2, then the rank is going to be what? It's going to be 2. Right, let us look for B. Let us look at for B. Now the determinant of B, let me just write this matrix here. It is 1, 3, minus 5, 1, 3, minus 5, 6, 7, 6, 7, negative 5, negative 5, 1, and 8, 0. 8, 0. Right. Use any row here which can give us that has the most 0. Actually use the last row. So I'm going to have 7. If you use the last row, I'm going to have 7, 3 minus 5, negative 5, 8, minus 1, 1, 6, minus 5, 8. If you find the determinant here, you're going to have 45. Or if you use this column here, the third column, I'm going to have minus 5, which is 6 minus 5, 7, 1, minus 8, which is 1, 3, 7, 1. Your answer still here is going to be still 45. You use any column or a row to find the determinant. Because matrix B, straight away, minus 45, sorry, it's minus 45, straight away gave us a determinant. We will waste no time. We will just say the rank of B is equals to 3. Because we have 3 different rows. Now, that is the rank of a matrix. That is the rank of a matrix.